Welcome to the second video in my help series, breaking down the most commonly confusing and conceptually difficult topics in GIS. This one addresses specifically datums and geoid models. So again, that's me, Dr. Mike Harmon, Program Director of the Online Masters in GIS and Spatial Analysis. I'm a teaching associate professor at Western University. That's my contact information. Hit me up if you have any questions. Or if you're looking to start a master's program online, remotely, there'll be more details of that to follow. So with datums and geoid models, what really gets students cooking? Well, datum shifts, the differences between horizontal and vertical datums, and then transformations. That's the three things that really confuse students the most. So a review from the first video, geoid, gravitationally defined surface of the Earth, specific ellipsoid measured by its major and minor axis. That would be the long and short axis of the shape. It's mathematically perfect, but it does not perfectly match the surface of a geoid. So what do? We create a datum where we take those centers and we move them around so that that surface now aligns better with at least part of the surface of that geoid, and we call that a datum. So then we can take that specific ellipsoid once it's been, realigned, and apply lines of longitude and latitude to it to create a GCS, and from that we create a PCS, projected coordinate system. So that's the whole underpinning of all the stuff that's going on. What is a datum shift? Well, when we're in one datum, for example, NAD27, and we switch to a different datum, like say NAD83, there's a shift in the coordinate values for the exact same real-world location. And students have a hard time sometimes just getting their head wrapped around this. They think that if your coordinate location is, 37 degrees, 15 minutes, and 28 seconds in one coordinate system, that it'll be the exact same in another. That's not the case. In theory, that real-world location could have an infinite number of correct coordinates for that location, as long as each correspond to a different datum. And this happens because each datum uses a slightly different ellipsoid shape and a slightly different alignment to the model of the Earth, and collectively that means that once you start drawing the central meridian and the equator and measuring out from these things, you're going to end up with slightly different numbers. In some cases, significantly different numbers. So here we have the same sort of ellipsoid overlay on the geoid with paired centers on the left. And what happens when we try to align them? Okay. All right, we have two different ellipsoids, different major and minor axes, because if you look on the right over here, the top one is more rounded and the bottom is more oblate. In other words, it's flatter in the top and bottom a little bit. And so we have two different alignments, in other words, focusing on different regions, different global regions. The top one looks more at the left side, if you will, of the geoid, and the one on the bottom is more concerned with the top. And I want you to focus to the location inside the little yellow circles, and you'll see how those overlaps are very different because of the alignments. That is a datum shift. Okay? What that is showing is when you have a different datum, in other words, either a different ellipsoid or a different alignment to a different part of the geoid, it moves things around. And so if you were to draw coordinates on either of those two spheroids on the right, that location inside that circle would have different numbers. Same location, different numbers, and that shift in those numbers is what happens when you change from one datum to another. Horizontal and vertical datums. The problem with this is the language that is often used to describe parts of these is very similar, very nondescript, and not super detailed. And to come up with a appropriate language that is neither not too complicated that no one can understand it, or too simple that it doesn't adequately explain it. So I'm going to try to do that, and hopefully this will help. Alright, so horizontal datum. First, it defines the reference surface ellipsoid for XY positions on the Earth. This would be things like WGS84, NAD83, NAD27. We use this for mapping distances, areas, locations, that kind of stuff. The vertical datum defines a reference surface specifically for the Z, or the elevation values. This would be like NAVD88 or EGM96. They are used to measure heights relative to mean sea level or another reference surface. Now, this is a very complicated concept, and I'm going to describe it and define it in two ways. I'm going to give you a simplified version that loosely fits how both of these work. And then I'm going to go into a more nuanced explanation to try to tease out the subtle differences between the two so that you more fully understand the process as a whole. So let's go to simple first, okay? We model the Earth based on the geoid, then we choose a specific ellipsoid and align it to match the Earth as best as possible, either globally for the entire Earth or for a specific region or part of the Earth. Alright, that makes sense. Now this alignment can be done by either shifting the ellipsoid's center relative to the Earth's center, that's local versus geocentric datums, or by tilting or rotating the ellipsoid slightly to fit the region better, aligning with surveyed control points on the surface, or using a combination of these techniques. So either we move the centers around to get things lined up, or we tilt and pan and spin until we get it lined up sort of in a certain place. And we can do that with these centers or with referenced fixed points on the surface that we want to align to fixed points on the other surface. Now the result of this is that we end up with a datum, and that allows you to describe locations horizontally, vertically, or even both. So this simplified explanation kind of works for both of these, in that it is more or less what happens, but not 100% specifically, perfectly, exactly. So if we go to the nuanced version on the horizontal datums, we fit the ellipsoid, okay? And to do that, we're going to choose the size and flattening, so that's basically the major and minor axis, so that it best matches the average shape of the geoid, either globally or locally. So we're going to use this geoid to help us pick out the best ellipsoid that we can. Then we're going to align it, and if it's global, then we'll do a geocentric, in other words, from the center. And if it's not, and we have to rotate it or spin it around, we might end up using some sort of a tilt or shift that involves, reference points on the surface. Once the ellipsoid is chosen and we get it positioned, we draw the longitude and latitude grid around it in that fixed position, and that creates our consistent coordinate reference frame that everyone can use. So how does this differ from the simple version? Well, technically we're not so much fitting it to the geoid exactly as we are fitting it to the mass of the Earth. But we're kind of aligning it to the geoid surface. It's a subtle difference. You could argue that it's not a difference, and I wouldn't fight you on it. You could argue that it's an absolute difference, and I wouldn't argue with you on that. But I think it is so very similar to what the simple version is explaining that it's really not worth struggling too much unless you are actually studying geodesy, in which case I'm sure they're going to give you a better explanation than what I just did. Now, horizontal. It's basically the same as the simple version, but the geoid is used mainly to select the ellipsoid, okay? Not to define the final position. The critical step is placing it in that fixed position, either globally or regionally, and defining that grid of longitude and latitude around it. That's the big part. Now with vertical datum, if we look at the nuanced version, it's a multi-step process. First, we have to figure out what is the ellipsoidal height. And this is what, for example, if you used a global navigation satellite system like GPS, it actually gives you an X, Y, and a Z. And it is that distance from the ellipsoid surface straight up in the air to where your XY coordinate point is in GNSS, measured space. There's also the geoid height. This is something that we call the correction. And it is the vertical distance between the ellipsoid that we just talked about and the geoid, or that mean sea level value, gravitationally based, that we've been talking about using through various aspects of these datums. And then last, we have our orthometric height. And this is what we call elevation. So elevation is a kind of a special thing. It is the height above the geoid. So it's what is the height of the surface above mean sea level. And if it's below that, then it would be a negative, for example, like Death Valley. Now, vertical datums, to continue, the simple calculation, big H equals little h minus big N. So your orthometric height, or your elevation, is essentially equal to the ellipsoid height, which here is represented by the white line, minus the geoid height, which here is represented by the yellow line. And so in places where the ellipsoid height is above the geoid height, you'll get, you'll get a positive value, and where it's flipped the other way around, you'll get a negative elevation. All right, so we use this in horizontal datums, in 3D surfaces, fixed positions. Every point on Earth can be described by X, Y, and Z's relative to that ellipsoid. When you measure your location with a sat nav of some sort, you get your own X, Y, and Z, but the Z is measured relative to the ellipsoid, not to the sea level, so it's not necessarily the elevation that you want. And that's why, an actual digital elevation model is a little bit more complicated. So, yeah, you need some consistent latitude and longitude, or projected XY, if you want to know where you are on an ellipsoid before you can really look up any vertical information. And so we use the X and Y that we get from the geoid model. They're basically grids or some sort of function that's keyed to a position. And the vertical datum surface is literally that geoid surface expressed in the same spatial reference as the horizontal datum. In other words, it's programmed so that for every location on one model, you harvest the other variable from the other model. Orthometric height is just the vertical distance from the geoid surface to the point on the terrain, like we've explained. Now, data transformations is that process of going from one coordinate system or one datum to another. And this is necessary because different datums place the ellipsoid in slightly different positions or orientations, or use slightly different ellipsoids. So it's important to do these things, because coordinates from the same physical point can differ by meters depending on the datums that's used. I believe if you look at certain locations like Esri's headquarters in Redlands, California, in NAD 83 versus NAD 27, depending on which one you look at first, and then incorrectly label it as the other, it will put Redlands, California out into the Pacific Ocean by a bit. So these changes are actually, can be pretty significant. Without transformation, data layers from different datums, they just won't line up. Transformations ensures that all the data sets share the same reference frame, so that in theory they will all line up. How does this all work? Well, we identify the source and the target, and we apply a transformation model. And that can be something like shift, where we move the origin of x, y, z to match the target, or rotate, where we align the axis if they're off a little bit or slightly tilted, or scale, where we change the sizes maybe a little bit of the ellipsoid. For vertical datums, this involves switching from one geoid model to another, adjusting the zero height to match the new definition. Uh, you'll get new coordinates, and the point now has an x, y, and z that are in the correct targeted datum. Essentially, if you really cook this all down, it's all math. Every datum transformation is just a set of equations that relates one coordinate system to another. Personally, I think like it's regression. We know a bunch of points measured in both datums, the source and the target. Using those, scientists solve for the best fit, whether we shift or we rotate or we scale. It's the math that's doing the conversion from one to the other. And when we apply a transformation, we simply apply that math. Once we have those equations, the old coordinate systems go away, the new coordinate systems are there. That's really all there is to it. Nothing's really moved. The only thing that we've done is placed stuff in a new coordinate system and then given it the new numbers that correspond to that change. So that wraps up this section. Again, if you're thinking about or interested in expanding your geospatial knowledge and skills, want to go back to school, want to get a master's, don't want to quit your job, don't want to move to another town, keep working, stay where you're at. Improve your GIS skills remotely with the online Masters in GIS and Spatial Analysis at West Virginia University. We offer virtual information sessions, typically 3 in the fall, 3 in the spring, sometimes 1 or 2 in the summer. The point of these are to answer any questions you might have and explain more about the degree program, the requirements, and all that. Don't wait another day if you're interested in going and getting your graduate education underway in a remote, asynchronous online format. Then check us out. Here's the link to our degree program. If you have any questions, you can contact me way back there on slide number 2 at the beginning of this lecture. You got my contact information. So hopefully we'll see you soon in the class. If not, hope this has solved some of your difficulty understanding what is in the eyes of many a very complex issue. Have a great day.